Okay, good morning. I hope everybody's doing well. Let's take a look. This week or today, we will look at some basics of programming. In particular, we'll look at conditional statements, those if-else statements, and also loops. And all of this stuff, I think you are familiar with and have seen already in Stats 20. But I think it's good to kind of talk about some of these things and talk about some of the details. A lot of this comes from these chapters in the different textbooks. And again, all of these things are available to read at no additional cost, as long as you're either connected to the UCLA network for this one, and this one's just free for everybody. Okay. All right, so let's start off with logical operators that produce logical values, because this is how we do all of our true false statements. All of our true false if else statements require kind of true false values. And so we have these Boolean operators or logical operators. So you've got or and not. And then you also have the exclusive or. And these are all kind of vectorized, meaning you can have a vector of x, multiple, true, true, false, false, or whatever, for x, and another vector for y, and it will kind of line up the elements and evaluate that. Okay. Meanwhile, you have the non-vectorized versions. You have the non-vector or and the non-vector and. So it's kind of the double vertical line and the double ampersand for the non-vector. And these ones only accept logical vectors of length 1. Okay? So these ones you can have length however long logical vectors, and recycling and coercion applies there. These ones only accept length 1 vectors. Okay. If x has a length greater than 1, it will return an error. Okay. And if y has a length greater than 1 and is evaluated, it will return an error. Okay. If y is not evaluated, even if it has a length greater than 1, if y is not evaluated, R is not going to evaluate it and it's not going to care. There will be no error. Okay. This behavior changed in version 4.3 of R. So if your version of R, like when you start up R and it tells you like what version it is older than that, you should update. You should update to the latest version. Okay. So here I've got X is true, true, false, false. Y is false, true, false, true. We'll use the vectorized or, and or, evaluates to true as long as one of the values are true. So true or false, it lines that up. That's going to be true. True or true is true. False or false. Both of them are false, so we're going to get false. And I got false or true. That's going to evaluate to true. Okay. As far as the and goes, this is vectorized, and so it returns a vector. Both elements have to be true for the and statement to be true. So true, false, true and false is false. True and true is true. False and false is false. False and true is false. Okay. Here I've got the non-vectorized or. X has a length greater than 1, so that's going to lead to an error. When you have the non-vectorized or and you try to evaluate that, it's going to say, hey, length is 4, and we're trying to coerce it into a logical vector of length 1. So that leads to an error. Okay. Here I've got false and non-vector, and then I have y. So y has a length greater than 1, okay? But it doesn't result in an error because y isn't evaluated at all. It says false and then r is just like, oh, if you got a false and something else, it doesn't matter what the other thing is. As soon as I know it's false and, I know the answer is going to be false. It doesn't matter what y is. So it doesn't even bother even looking at y. Okay, well, R doesn't even look at y, and it just says, oh, right away I know it's false. Okay, same kind of idea. If you got true or, what R doesn't even look at this vector y. It just says, oh, true or. Okay, it doesn't even matter what you're going to say next. Okay, as soon as I hear true and or, I know the answer is going to be true. Okay. But if you got something like false or y, then R is like, okay, well, I got to evaluate y. And it goes, uh-oh, y has a length greater than 1. I don't know the answer, or I don't know what to do here because I'm trying to coerce it into a logical vector of length 1, and it can't do that. So that's what we have. All right, here's just a little kind of self quiz for yourself. Okay. What what is true or NA? True or NA? What is that going to evaluate to? True or missing? Okay. All right, what about true and missing? And then you got false or missing, and then false and missing. So yeah, true or missing, it doesn't matter what the missing value is. It's going to be true. Okay? True or whatever is over here, it doesn't matter. That's going to be true. True and missing, now it matters. Is the missing value a true? Is the missing value a false? We don't know. So the answer is we don't know. Okay? The answer is NA. Okay, false or NA. All right, again, it matters what the missing value is. Is the missing value true or false? We don't know, so it's NA. But then if you got false and NA, all right, false and a missing value, it doesn't matter what the missing value is. We know the false and whatever that value is going to evaluate to false. So you can still get true and false values even with a missing. Okay, we have exclusive or. Exclusive or means one thing has to be true and the other thing has to be false. But if both things are true, exclusive or doesn't work. And then if both things are false, obviously that's not going to work either. Okay, so and exclusive or is also vectorized. So I've got X, true, true, false, false, NA, NA, NA. And then I've got Y, false, true, and then true, false, NA. So this evaluates to true when you have X is true and Y is false, okay? But if X is true and Y is true, okay, that exclusive or is false, false and false, false exclusive or false is false, false exclusive or true is true, and then exclusive or with any kind of missing value, because it matters, exclusive or always evaluates to an NA. All right, any and all are generalizations of the or and, but it accepts vectors of more than two, right? So you kind of have this vector here. I've got three values in U, V and W, and we can do any. So are any of the values true? Okay, it's kind of like or, true or true or true. Yeah, that's true. Okay. Are all of the values true? Are all of them true? That's also true. Okay. Here I've got a mix, true, true, false. Are any of the values true? That's going to be true. Are all of the values true? This evaluates to false. Okay. And then I got false, false, false. Are any of the values true? Nope, that's a false. Are all of the values true? Nope, that's going to be false. So that's any and all. Uh, Here's something interesting to think about. Okay. And that is when you have a length 0 vector, okay, like logical length 0, zero length logical, or null or something. And if you kind of combine that with, some vector v, it shouldn't change the results if you were to evaluate v. So with that in mind, what do you think any on a length 0 logical vector would return, or all on a length 0 logical vector returns, right? So what I'm trying to say is that let's say you had a vector v, okay, and you evaluate any on v, you get some kind of answer. If you mixed in a null or a logical 0, it shouldn't really affect what v is, okay? So if you call any on logical 0 v, it should produce the exact same result as any on v by itself, okay? So with that in mind, what should any on logical 0 return, okay? Is that going to be true? Is that going to be false? Is that going to be NA? What do you think? So it might be a little bit surprising, but when you call any on, so any is kind of like the equivalent of the or, any on a length 0 logical vector returns false. Okay, any on a length 0 logical vector returns false. So let me just kind of demonstrate. Here I've got true, true, true. Any on U by itself returns true. Okay, if I were to mix in the false in here, okay, the X in with this, that still returns true. Okay. Um, Here I've got true, true, false. And if I were to mix X in here, okay, So any on V here returns true. And if I mix in X, all right, the length 0 of the thing, that still returns true. Okay. Here I've got false, false, false. All right, W is false, false, false. If I call any on W, I get false. Now, if the length 0 evaluated to something other than false, the result here would change, right? Like if any on the length 0 were true, and I do any on X and W, that would suddenly change to true. Or if this evaluated to NA, that would also change to NA. So in order to kind of prevent this from changing, okay, because we're really adding nothing, right? We're adding like a null statement to it. The any on the any on the length 0 needs to be false. Okay. And then with a similar kind of logic, all applied to a length 0 vector evaluates to true. Okay. All on the length 0 vector evaluates to true. And again, here I've got U is true, true, true. All on U by itself is true. But if X, the length 0, evaluated to something other than true, that would change the result of this. The all on the X and the U mixed together. If that were, if this evaluated to false or NA, this would change the answer there. Okay. These other ones, they all evaluate to false, and that's not going to be a problem here. Okay. So, something to keep in mind as far as any and all and length 0 vectors. All right, we have some comparison operators. Comparison operators produce logical values, and I think we're familiar with these. You test for equality. Is X equal to Y? Or is X not equal to Y, less than Y, greater than Y, less than or equal to, greater than or equal to? And then you also have the in operator, okay? And all of these are vectorized and they perform recycling. So, if you compare X and Y and you've got different kind of lengths, and it's going to recycle the shorter one to kind of match the other. More details that they helped, okay? If you're So, we normally think about like numerical values for X and Y, and we can kind of compare those things, but you can also kind of compare strings or characters, and in that case, the less than greater than is checking to see like which one comes before the other in the alphabet, okay, if you were to alphabetize these things, okay, which is fine and dandy when you're dealing with letters and words, but sometimes if you have other symbols like numbers and things like in there, then it can get a little bit weird. And so a couple kind of interesting side effects, I guess, or things that happen is the character string 10 comes before 2, the character string 2. So, when you're talking about characters, 10 comes before 2 because 1 comes before 2. So, this statement is true, is character 10 less than character 2. That's true. But of course, if you say these are numbers and this represents 10 and this represents 2, obviously 10 is not less than 2, so that's going to be false. Okay, and as far as the symbols go, they follow the ASCII chart. Okay. And this is the ordering of symbols in ASCII, and that's what we have there. Okay. All right. We also have a bunch of is functions, and these just check the type or the class or whatever it is. So, is something missing? Is something null? Is something logical? Is something double? Is something a matrix or an array or data frame or a function? You have all of these things, and they'll return true or false for whatever object is in there. Okay, let's talk about how to use these with conditional statements. All right, so conditional statements kind of power all of our coding pretty much. So we have these if statements, and if it's true, then it's going to evaluate the certain chunk of code, and if it's false, then it doesn't. And so you're going to have an if condition, and that condition must be a length 1 logical vector, and it cannot be missing. All right. If you have a condition greater than length 1, that's going to result in an error. If it's not logical, it's going to try to get coerced into logical if possible. If the condition results in a missing value, you're going to get this error, missing value where true, false needed. Okay. If the condition is length 0, you're going to get a different error. You're going to get argument is of length 0, right? And again, I want you guys to get into the habit of reading your errors, right? When you encounter an error message, it should give you an idea of what went wrong. And so when you see these error messages, this is what went wrong. So missing value or true, false, that means you have an NA in your if statement. Argument is of length 0. It means you've got a length 0 condition, okay? And then after the if statement, you put in yeah, curly brace, and the lines of code associated with that inside the curly brace will get run when the if statement is true. All right, so here, very silly kind of simple example. I got x is 1 and 3. Is 1 in x? That's a true statement, okay? So if I plug that into an if, I got if this condition, if 1 is in x, then execute this code. Well, this is true, so it's going to execute the code. It executes the code and it prints out hello to the screen. All right. Over here, though, I changed my comparison operation into something, and this returns a vector. So I've got x is 1 and 3. I ask, is x less than or equal to 2? So it's true for the 1, it's false for the 3. And if I throw that into my if statement, I have if x is less than or equal to 2, then print hello again. But in this case, because I've got a vector of length 2, all right, so I've got a if true, false. R doesn't know what to do with that. So it says, hey, the condition you've provided me here, this thing, it's got a length greater than 1. The condition has length greater than 1, or it gives me an error, okay? So, what do you want to do with a statement like this? Well, if you've got something like if this conditional if this logical comparison, this comparison results in a logical vector of length greater than 1, you can throw it into either any or all, okay? So are any of the values of x greater than 2, greater than or equal to 2? That's true. Or I could say, are all of the values in x greater than or equal to 2? Then that would result in a false, okay? But that would be a length 1 thing, all right? So here I write, if any of the values in x are greater than or equal to 2, then print, can you hear me now? And that evaluates to true. It prints out the statement. So that evaluates and that works, okay? Sometimes you run into this issue. Oh, you know what? I was about to forget. Let me give you your first view quiz answer. So this is week 2, Wednesday, and your first answer is the letter E. E as in elephant. E as in elephant is your first view quiz answer. E. Okay, so here x is the vector 1, 2, 3. And I'm going to do if x subset 5, okay? So x subset 5 is asking for the fifth element in x, and there is no fifth element in x. And so if you remember, what out of bounds with an atomic vector returns NA. So now I've got is NA greater than or equal to 2, that is going to evaluate to NA, right? So here I get this error message, error, missing value or true false needed, okay? This is a really common error that you run into, and it means you've got an NA, all right? So something either evaluated to NA, or you know, you've got like an out of bounds issue or something. Um, out of bounds with an atomic vector results in NA. So in this case, you get an NA, so this doesn't work, okay? Um, so you got to check, why are we getting NA? Okay, sometimes you have the result produces a length 0 vector, okay? A length 0 vector, and you know, you get a length 0 logical thing. So here I've got x is 1, 2, 3, and then I run this function, which x is equal to 4, okay? Well, none of the values in 1, 2, 3 are equal to 4. And so the result there for the which statement gives me integer vector of length 0, integer 0. And then so if I throw that into here, which x equal to 4, is that equal to 4 or whatever? If that, so this is going to be a logical vector of length 0 because I've got an integer length 0. So this evaluates to logical 0. And this doesn't work either, okay? I get an error, okay? It says error in if this argument is of length 0, okay? So, you know, you'll probably encounter some some kind of error message. And again, read through the error message and familiarize yourself with what these error messages mean and where to start looking in your code to troubleshoot. And a lot of times it's going to be in an if statement if you encounter any of these things. And then, if your if statement is looking at some kind of value, you want to see like, okay, what is the value of the thing when it went into the if statement? We can nest our conditionals. All right. So this is kind of like using else and else if. So if you want to use an else statement, there has to be kind of a preceding if statement, and that the else only gets evaluated when the preceding if statement is false. Okay. Um, and and so for in R, the else if is done by doing else, and then you have to put if on the same line. So here I've got x is the value 3. We're going to do if x is less than 0, print negative. Else, if that's false, then check if x is greater than 0. And if that's the case, print positive. And if that is also false, then print 0. So here, this is false, so it skips over. This is true, x is greater than 0. That's true, so it's going to print positive. Okay. Here, I've got x is 0. This is false. X is less than 0 is false, so it skips to the next statement. If x is greater than 0, x is not greater than 0, so that's false. So it hits the last else statement and it prints 0. Okay. Here I've got a statement, and this kind of, sometimes we write things like this without realizing this is what's going on. Here I've got x is 3, and then I got this if statement. If x is greater than 0, print positive. Okay. And so when it runs, this evaluates to true and it prints positive, and then it's done. Once the if evaluates to true, it's going to skip any of the else statements. Okay. The else statements only get looked at. They only look at this stuff. Okay. When the original if is false. So this thing, else if x is greater than 1, okay, this will only get looked at when this statement is false, okay? So if x is less than 0, less than or equal to 0, then it looks at this. And then there's no scenario where x is greater than 1, but this statement up here is false, okay? So this print bigger than 1, this will never get evaluated. This will never happen because there's no value of x where this is going to be false, but this is true, okay? So either we're going to get positive or not positive, but this one's never going to evaluate. One thing to remember is that if is not vectorized. Okay, if always requires a logical value of length 1, and if you give it something longer than 1, you get an error. Okay, so functions that use an if you cannot be given a vector of values. Okay, there is another function called if else, and if else is vectorized, and it requires 3 arguments: a condition, a test, the result if the condition is true, and the result if the condition is false. And here, this is just a very simple example. This one's not even vectorized. But if you've got something like if x is equal to 5, and you want like what happens when it's true versus what happens when it's false, and you want to kind of store these results, you can kind of reduce it to this. If else x is 5, what happens when it's true versus what happens when it's false, and we can store that into n. I'll show you another example of if else later on. where we can kind of start to understand kind of the vectorized nature of if else, which can be used to kind of make things a little bit more efficient. Okay, let's talk about loops. All right, so loops are super handy and super useful, and we use them quite a bit. Now, one word of caution, R, when it comes to loops, R is not the fastest or most efficient language. But again, loops super handy and super useful. So we use them quite a bit. Okay. Now the most kind of common and simplest loop is the for loop. Okay. And you give it a vector, and R is going to run the same bit of code that's inside your for loop. It's going to run it for each element in that vector. So a very kind of common thing I've got for x in 1 through 10, it's, for the first iteration of the loop, x is going to take on the value 1, it evaluates the code, then it goes to the next iteration. X is the value 2 and evaluates the code, and then x is the value 3 and evaluates the code, and goes on until x reaches 10, and then it stops. So the line of code that gets evaluated is cat x squared to the screen, okay, and then put in a space, and then that's it. So cat just kind of, it's similar to print, but it's not print because print does some formatting and cat just outputs raw output to the screen. So, but anyway, we get 1 squared, 2 squared, 3 squared, all the way up to 10 squared, and then it quits out of the loop. Okay. Now, this is kind of the most common thing that we pass for a for loop is just some vector of integers, but you can pass it any kind of vector. All right. So here L is a list. And remember, lists are also vectors. Okay, they are generic vectors. But here I've got a list, a list of length 3, train of 3 cars. First car has 1, 2, 3. Second car has A, B, C, D, E, F, G. Third car is true, false. And we can say for Y and L, right? So for each element in the train, basically in the list, we're going to say print length of Y. And so it looks at the first train car and says, ah, that thing is length 3. Second train car, that thing is length 7. It prints 7 now. And then the third train car looks at that, and it says the thing in there is length 2. Now, notice when we say for Y and L, it is extracting the actual element from the train car. It's not saying the first the first thing is a train of length 1, because it's not printing 1, 1, 1. It's not saying train of length 1, train of length 1, train of length 1. Okay, it's saying the contents of that first train car, of that first list element, is this element, is this vector of length 3. The contents of the next thing, okay, in the list is length 7, and then the contents is length 2. So for Y and L, it's actually extracting out the element from the list there. Okay. But yeah, you can in a for loop, it feels a little bit strange because we're often used to just seeing these kinds of for loops, 1:10 or something, but you can provide any kind of vector, right? Here's I'm gonna give it an atomic vector. It's a character vector, and we can say for state and state name. So um there's some built-in data sets in R. You can call just library data sets, and you just do something like state.name, and that will have all 50 states of the US. And so, in alphabetical order, we have Alabama, Alaska, Arizona, Arkansas, and California. And so for state and state name 1 through 5, we're going to go through here, and we're going to just cat the state. Okay, Alabama has number of characters in Alabama, 7. Okay. And then cat letters in its name, period, new line. And so when we iterate through this, runs it for Alabama. It says Alabama has 7 letters in its name. Then the next iteration of the loop, it runs for Alaska. Alaska has 6 letters in its name, so on and so forth. And we have that. Okay. Now, as far as loops go, we often want to store, do some kind of operation and store the results of that operation somewhere. And if you're going to do something like this, the best way to go about it is to create the object where you're going to store your results. Okay. Create that object and then fill in the values. So here, just to kind of illustrate the speed difference, I'm going to do like 10 million, 10 to the 7, 10 million values. I'm going to do x squared. Okay. And we're going to store that. And so here I create an empty I repeat NA 10 million times, and this is going to create my vector results. All right, so I have a place to store everything, and then I run this for loop for x in sequential and long results, take x squared and then store it into results subscript x. Okay, so it does that. It takes me less than a second, 0.64 seconds on my computer. Sometimes you don't know how many values you're going to get. So you just start off with results as 0, and then you just kind of run along. And then when it's done, as it's going, you just kind of grow the thing. Okay. So the first time it takes the first value and stores in it. And then the second time it has to resize this vector from length 1 to length 2. And then the third time it has to resize it from length 2 to length 3 and so on. And so it has to kind of do some resizing every single time. And so that takes a little bit longer. So, this takes 0.64. This takes, over 4 times as long. It takes me 2.83 seconds. Okay. And so here I do for x and 1 through 10 to the 7, and it does that. It takes me 2.83 seconds. Okay. The worst, the worst offender here is to kind of copy your results, to append and copy and replace. So here I start off with results as an empty vector. And then I'm going to say, with each iteration, basically append x squared to the results. Okay, combine results with x squared, and then store that back in results. Okay, so sometimes I see this in students' code, and it always makes me cringe a little bit. But we have that. And you'll notice how long this takes. And here I only did 10 to the 5, so only 100,000, 1/100th of here I did 10 million, and here I just do 100,000. But even just doing 1/100th of the work, it takes 13.64 seconds. And if I tried to do it for 10 million, I would have been sitting at my computer for a really long time just to kind of tell you that it takes a really long time. So I didn't bother doing that, but here you can see that this is the least efficient. Okay. So if you know exactly how long it's going to be, do this. If you don't know how long it's going to be, then this is acceptable. But you should really never do something like this. Okay. Um, the other kind of really common loop that we have is the while loop. Okay. And the while loop repeats the code until the given condition. So there's this conditional statement here. When this condition is false, it doesn't repeat it. Okay. So while, and then if this statement is true, it evaluates the code. If the statement is false, it stops. Okay. So here I have I as 1. We're going to do results. We're going to take 10 of these things. Okay. And I'm going to say, while I is less than or equal to 10, evaluate 10, I squared, stored into results subscript I, then add 1 to I. Okay. So when I run this, it goes from I is 1 through 10. Okay. And it gives me 1 squared, 2 squared, 3 squared, up to 10 squared. When this code has finished, right? Because what is the value of I when the code finishes? Is it 10? Is it 11? What is the value of I? What do you guys think? Okay. In this case, the value of I is going to be 11. Okay. Because what happens is it runs it. So, it does 9. Okay. I is 9. 9 is less than or equal to 10. It stores 9 squared into the ninth spot. 81 goes into the ninth spot. Then it gets I becomes 10, right? Is 10 less than or equal to 10? That's true. So it does 10 squared, and that stores 100, stores it into the 10th spot. And then it adds 1 to I. I becomes 11. And then it goes back to the top of the loop while I is less than or equal to 10, checks if 11 is less than or equal to 10. That's false, so it stops. It kicks out of the code. So it evaluates 11 less than or equal to 10, that's false, and then it doesn't run the code. So I is 11, the last result is I squared, 10 squared. Okay. Related is the repeat loop, okay? The repeat is kind of like while true. So instead of a conditional, it's just kind of like while true. So that just runs forever, okay? Okay, repeat just runs forever. And so um, you need to have some kind of statement in your repeat loop that has a break, okay? Otherwise, your repeat loop is going to just repeat forever, okay? So repeat repeats until it hits break, okay? So here, the equivalent of kind of that while statement is here. Now it does this, and then I have a condition inside the loop where I just check if I is greater than 10, then you break out. Okay. If I is greater than 10, then break out. So here, I start off with 1, and then when I becomes 11, it'll check if I is greater than 10, that's true. Then it hits break. And when it hits break, it quits the loop. All right. So again, it prints 1 squared, 2 squared, up to 10 squared, up to 100. I is now the value 11, and then it breaks out. All right, so some keywords that are important when we're dealing with loops are break and next. Break ends the current loop entirely, whereas next just ends the current iteration and then starts the next iteration. It just kind of skips the rest of the code. So here I've got some code. I say for I in 1 through 10, if I is divisible by 2, so I mod 2 is equal to 0. If that's true, then break. And then outside of that if statement, I've got cat I. So I is 1. So when we run this, it starts off with 1. This is false, so it doesn't evaluate break. It's going to cat 1 to the screen. Then it goes to the next iteration of the loop. We get 2. This statement is true. 2 is divisible by 2. 2 mod 2 is 0. That's true. So it hits break, and then it quits the loop. And so when we run this code, we just get 1. 1 gets output to the screen. It hits 2, and then it quits out. It doesn't even bother looking at 3, 4, 5 through 10. What if I run the exact same code, but instead of break, I run next? Okay, so instead of break, I replace next. Well, what happens here is every time it hits next, it just skips to the next iteration. Okay, it ignores any of the rest of the lines in the loop. So it starts off with I is 1, and we get 1. This is not true, so it cats 1 to the screen. Then it goes, it hits the end of the loop, so it goes to 2. Well, 2, if 2 mod 2 is equal to 0, so that is true, so it hits next. When it hits next, it skips the rest of the code and goes immediately to the next iteration, 3. Then with 3, this is false, so it doesn't evaluate next, and it cats 3 to the screen. Then it goes to the next iteration, 4. 4 is true, it hits next, and it immediately jumps to 5. Okay, it doesn't look at the rest of the code. And so when you run this, it outputs just the odd numbers, 1, 3, 5, 7, 9. Okay. Okay, versus back here, when it hit break, it just quit. All right. We have sometimes you can use something like sequence length or sequence along, and this allows you to kind of work with certain elements and store things in the results. And so here I've got the list, and I'm going to extract out the first element, then the second element, and the third element. And so sequence along L is a length 3, so sequence along L produces 1, 2, 3, and I can kind of produce similar kind of results, and this way I can store it into results 1, results 2, and results 3. Okay. Now you might wonder, like, why do we have to bother, right? Can't I just do 1 colon length L? And this is probably super common and super handy, or just a quick shortcut that we write. And I can say I can just do like 1 colon 3, right? 1 through 3, 1 length of L, whatever length L is, and this works, okay? And if I did sequence along L, L is length 3, and so produces 3. I could do sequence length of length 3, of length L. So sequence length of 3 also produces 1, 2, 3. So you feel like, well, all three of these things produce the same kind of thing. Why, for me, it's just easy to think of like 1:3. That's like the super easiest for me to think about. Why don't I just use that? Okay. Well, the problem arises when L is length 0. Okay. So what if, in the previous parts of your code, the result ends up being 0 length? Okay. So here I have an empty list, a 0 length list. And if I did 1: length L, it produces a vector 1, 0. Okay. 1, 1, 0. And then if I try to subset L using double square bracket X, okay, here I'm doing L, give me the first element of L. That doesn't exist. So I get this error, subscript out of bounds, subscript out of bounds. Okay. So using 1: length L, this could result in problems if you have a length 0 list. So um, using sequence length or sequence along avoids that issue. So here, if I have an empty list and I call sequence along L, I get a 0 length integer vector. All right. And if I run a for loop using a 0 length integer vector, nothing gets executed. Okay. So I don't run into any problems here. Nothing gets evaluated. Similarly, if I call sequence length and it's a 0 there, I get a 0 length vector. And again, nothing gets evaluated. All right. The problems arise when you try to evaluate something here and there's really like no no values there. So you get errors over here. Here, if you call a for loop on this, nothing gets executed. So this avoids the issues. So when you're running just a quick little script, this often works. One colon length L, that often works. But if you're writing a function, yeah, you need to kind of take into account different kinds of things that could happen. You should generally always use sequence along or sequence length. Okay, let me give you your second view quiz answer, which is the letter C. C as in cat. C as in cat is your second view quiz answer, C. All right, let's talk about vectorizing code, okay? So this is just to say sometimes it's not worth vectorizing or trying to make your code more efficient. Students often ask on campus wire, will we be graded on efficiency? And the answer is no, okay? If your function works, even if it's inefficient, if it works, then I'm happy with that. You should be thinking about efficiency though, okay? You should try to find more efficient ways to write your code. And as you write more and more, you're going to get better at it, okay? But yes, sometimes it's better to write inefficient code that takes 20 seconds to run than to be stuck for a few hours trying to write, efficient code. Okay? All right. But anyway, let's talk about vectorizing our code because that will make things a little bit more efficient. So let's say we have this piecewise function, this mathematical function. It's piecewise. It's negative x cubed for x less than or equal to 0. It's x squared for x between 0 and 1. And it's square root of x for x greater than 1. Okay. To write this using an if statement, I can write f is a function of x. If x less than or equal to 0, then the value that we want is going to be negative x cubed. Else if x is less than or equal to 1, then the value is going to be x squared. And notice I don't need to check if x is greater than 0 because this is only going to get evaluated when this statement is false. And when this statement is false, that means x is greater than 0. And then lastly, I have another else. And so if this is false and this is false, then x is greater than 1, and we're going to do square root of x. That's going to be our value, and then the function is going to return our value. Okay, so here's our function. Because it's got if statements, it is not vectorized. And so if you give it a vector, you get an error, right? So here, let's say I wanted to evaluate this function from -2 to +2. Step size 0.01. So -2, -1.99, -1.98, all the way up to, 2. This is a vector, if I plug that into my function f, I get an error because f is not vectorized. I get a error. It says error. The condition has length greater than 1 because X is a vector of length, 400, 401, and it can't handle that. Okay, so if I try to plot that, it's not going to work. So what we have to do if we have a non-vectorized function is we have to kind of extract out the values one at a time, plug it into the function one at a time, and then evaluate it that way. So here I've got my vector x, length 401, and I'm going to throw it into a for loop. I'm going to say for I in sequence along x, then subset x to just that ith value, plug it into f, so f of x sub I, and then take that result and store it into plot values sub I. Okay, so now I'm going to store the result into my vector plot values. And this works because it goes through the loop, right? And it does one element at a time, and it plugs it into the function, and it gets that, and this is the resulting function. So that works, okay? But again, for loops in R, just loops in R in general, are not the most efficient thing. So we can vectorize it and avoid loops. And again, you have to just ask yourself, is it worth taking the time to vectorize it? Sometimes the answer is yes. All right. So we can vectorize it using if else. Okay. So the way we're going to do if else is we're going to run the statement. We're going to check the logical statement. If x is less than or equal to 0, then um, return negative x cubed, okay? And if it's not, then we will nest another if else. We're going to check if x is less than or equal to 1. And if that's true, then return x squared. And if it's not true, return the square root of x, okay? So this is basically doing the exact same thing here, but it's using if else statements, okay? And it's vectorized. And if I kind of remove the codes and make it compact, now I got if else x less than or equal to 0, negative x cubed when it's true. If it's not, evaluate this if else statement, and we'll check if x is less than or equal to 1. And if that's true, give me x squared. And if it's not, give me square root of x. Okay. And this is vectorized. So here I can have the vector x goes from -2 to +2. And then I plug that into my function. This is the function f2. I plug that in and it works. Okay. I don't need to run a loop to extract out each element one at a time. It's vectorized. It applies it to the entire thing and it produces the result. I can plot it. Okay. I do get a warning here. It says warning, square root of x nans produced. Okay. And so the way if else works is that it evaluates all of these it evaluates all of the statements simultaneously. Like if you look at the statement if else x less than or equal to 1, x squared and square root of x, what it's doing is it's evaluating the entire vector x less than or equal to 1, and it's getting a bunch of true false values. Then it evaluates x squared and it gets a bunch of true false values. Then it evaluates square root of x and it gets a bunch of true false values. So for example, let's say I don't know. I'm just making up. Okay, so let's say x is like -2, um, -1, 0, 1, and 2. Okay, and then so if my statement is we're gonna do if x is less than or equal to 0. Okay, this is going to be true, 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 false, and false, and then we can do x squared. All right, versus square root of x. Okay, x squared will give me 4, 1, 0, 1, and 4. And then the square root of x, so this is going to be x squared. And then the square root of x, I've got na, 0, 1, and then, 1.4, 1.41. And this is square root of x. Okay. Um, and so what it's doing is it evaluates all of these things, and then it takes basically the if true, and then this is if false, right? So then it matches them up, and then so the result is going to be 4, 1, 0 because these correspond to the trues, and then for the falses it gives me 1, 1 and 1.41. Okay, so it evaluates the entire vector for the logical statement, And then it evaluates the entire thing for x squared and evaluates square root of x. And then it's just that these things are producing NAs. Now we don't see any NAs in the results, um, but they are evaluated and they just kind of look to match them up. Okay, so that's where you're getting NAs. So it's vectorized, it evaluates the entire thing and it just kind of matches them up. All right, these remaining few slides you can just kind of go on your own. We have operations row sums and column sums, and these are kind of super efficient. They're faster than using a loop. They're faster than using apply. If you do row sums or column sums, the amount of time that it takes is really quick. So if you're able to use row sums or column sums when dealing with a matrix, that's going to give you your quickest results. Okay, let me give you your last view quiz answer, which is the letter D. D as in dog, D. And that will be it. We'll end here for today. Have a good rest of your day, and we will see you on Friday online again. Same place, same time. We'll see you Friday.